Hey everybody, welcome back to the Professor's Du Bois channel. This is Corey and Victoria here, and this is the final installment of our equilibrium calculation series. We're going to call it the equilibrium six-pack series. And for this one, we're going to talk about reactions in the gas phase where the volume changes. And changing the volume is going to change the concentrations of the reactants and products. We're going to show you how that works.
So we have a question here where we have all of our products and our reactants are gases, so they will be affected by compression. So it says here that they're compressed at constant temperature. So we start out with a 17.1 liter flask. I've never seen a 17.1 liter flask, but that makes it interesting for the calculations. And we are given some molarities of our gases, and we want to know what the new concentrations are going to be if we change the volumes. So we're going to start right out with creating an ice table, and what we have to figure out what the new concentrations are. So we have our existing concentrations at the 17.1 liter. We are going to create an ice table, but we need to know what the new initial calculation, what the new concentrations are to put into our ice table. So I'm going to write just kind of scaffold up our ice table here, and then we'll show you how to calculate those new concentrations.
So the way we're going to go about this is we're going to take the molarity, and that's the big M, which is really mole per liter. So if we take that molarity and multiply it by the volume, the 17.1 liters, the liters will cancel, and we'll end up with moles of each of these species. And something that's kind of hard to wrap your mind around is that the number of moles isn't going to change. It doesn't matter what size the container is, you're still going to have the same number of moles. And you can think of this as number of particles, if that's easier to wrap your mind around than the term moles. But we want to calculate the number of moles, and then once we have the number of moles, we can divide it by the new volume, the 8.84 liters, and then that's mole per liter, and we're once again in molarity, and that's our new initial concentration. So for the COCl2, I've got 0.4739. Now, do you think we should walk through the other ones, or do you think they can do that?
I think they can do that. So that just this number will change. So we got that from here.
Yep.
And so for our carbon monoxide, we would put that number here and change it from 17.1 liters to the 8.84. So when we do that, we have our new initial.
It's 0.1250 for both the CO and the Cl2. So we have new concentrations, and these are not at equilibrium. So we can calculate a Q to see which way this is going to have to shift in order to get back to the equilibrium where the K is going to be equal to 1.70 times 10 to the negative 2.
And you can see that we calculate the Q exactly the same way as the K, because we're going to compare it to the K and see if it's greater or less than the K, so we'll know which way to shift it. So this is the 0.1250 squared. I'm just going to square it since it's both the same.
Okay.
And we get 3.30 times 10 to the minus 2. And we're going to compare it to this number. So they're both times 10 to the minus 2. 3.3 is greater than our K value. So our products over our reactants is too big. So we need to reduce this products over reactants. The only way to reduce that is to reduce our products and increase our reactants. So that tells us the direction of change.
Now there's another way we could do this, and we could think about this in terms of Le Chatelier's principle and pressure. So what we have ultimately done is we've decreased the volume, and by decreasing the volume with the same number of moles of gas, we've increased the pressure. So Le Chatelier's principle is going to try to reduce that pressure. Now if you look at this, there's gases on both sides, but there's 2 moles of gas on the right and only 1 mole of gas on the left. So the coefficients of this balanced equation are all 1s, and all I'm doing is adding the coefficients. So I've got 1 CO and 1 Cl2 for my product, so I add those together and I get 2. And on the left-hand side, there's only 1. So if we can shift this reaction to the left, we're shifting to the side with fewer moles of gas, which will help bring down the pressure.
Okay, so now we have our equilibrium concentrations in terms of X. We can put that into our K expression and solve for X. So K is
1.70 times 10 to the negative 2.
Okay, so 1.70 times 10 to the minus 2 equals our products over our reactants. So this is 0.1250 minus X times the same. And I'm not going to just say squared here because I know I'm going to need to FOIL this. And it's easier to see it if I have it right out.
Foiled again.
Oh, da-da-da. It feels like that. Okay, so first off, I'm going to multiply both sides by this 0.4739 plus X. So it gets rid of it there. And I'm just working with things in the numerator. I like that better.
Me too.
0.4739 plus X.
So we're going to have to distribute again. We talked about this in episode 2, I think, how to do this.
I think so.
Distribution. So we're going to multiply the 1.70 times 10 to the negative 2 times the 0.4739. That gives us 0.008056. And then we're going to multiply it by the plus X, and we get plus 1.70 times 10 to the negative 2x. Okay, over here we have to FOIL.
First,
episode 3.
Yeah. And what do we get? So the first 0.1250 times 0.1250 is
0.01563.
O is outer, so the outer ones.
So I get negative 0.1250x. Same for the inners. And then the last is negative x times negative x, which is positive x squared. I can combine those two x terms. I've got 2 that have an x, and if I combine those, I get negative 0.2500x.
Okay. Since we have a squared term, an x term, and just a regular number, we're going to need the quadratic formula. So we want to combine like terms and set it equal to 0. So if I
set 0 on the left because there were only 2 terms on the left.
Ooh, I like that.
So I just thought it was a little easier. So we're going to subtract the 0.008056 from the 0.01563. And that's 0.007574. Now I'm going to subtract 1.70 times 10 to the negative 2x. And I got to subtract that from the x term. And I end up with a negative 0.267x plus x squared. And we have 0 on the left because we can't cross that one off there. Yeah.
So
okay.
This is our
There's your C.
A equals 1. B equals a negative 0.267. And C equals a 0.007574.
All right, when we put this into our quadratic equation, or the quadratic equation solver, or our graphing calculator, we get 2 roots. The first one, 0.235. The second one, 0.0323. Neither of these roots is negative. You know, we were saying before, if you get a negative root, it often won't make sense. So we'll have to go back and look at our ICE table and, you know, does this make sense? Can we subtract 0.2 from 0.1, 0.1250 specifically?
minus 0.235 gives us a negative number.
That would be a negative value. So that one just doesn't make sense. That's the root that doesn't make sense. We're going to go with the 0.0323. That is x. So if we go back to our ice table and we put those values in for the equilibrium concentrations, we put that value 0.0323 where it says x, we get equilibrium concentrations
Okay, so where I got this, the 0.4739 was right up here. So I'm just putting them back into the equilibrium row.
Yep, substituting the x with the 0.0323. And our CO and Cl2 are both the same, and they are 0.0927.
Okay, I just wanted to write down what it was. So 0.1250 minus 0.0323 equals, plus there, and that is 0.0927 molar. So those are our three answers, because these are both the same.
Okay.
Fantastic. So we want to provide you with additional practice with answers. So
here's another problem.
Pause the video and kind of take a picture of this, or pause it and work through it, and we want to provide the answers for you.
Okay, so, and I'll just kind of talk for a second. It's a very similar problem, but here we have a small container, and we're making the container larger. So the pressure is going to decrease. If you're going to use Le Chatelier for your change, think about pressure decreasing. You can also calculate a Q when you get your new concentrations, your initial concentrations. Now, how are you going to get those? You're going to take your original molarities and multiply by that 6.12 liters to get the number of moles. And then you'll divide by the new volume, 14.4, to get the new molarities. Those will be your initial concentrations. You'll have to use either Le Chatelier or your Q to find the change. And I bet there's some FOILing and some distribution and some quadratic equation.
Go back to our other episodes if needed with help, for help with all of that. And these are the same. 2. All right.
Those are the new equilibrium concentrations.
There you have it. There's your series for equilibrium concentration calculations, and we hope this has helped. And leave a comment, like and subscribe. We are the Professor's Jew Boys. Stop back, stop often, and we hope we're helping you learn some chemistry. Have a good day.